So welcome to this second lecture on quantum physics and relativity. In the first lecture I have stressed that quantum physics and relativity imply each other. You cannot have one without the other. In this second lecture I go further discussing the relationship between space-time and quantum physics, or even more specifically between non-locality at detection and the quantization of the space-time. Consider the experiment sketched in this figure. We have a laser source emitting photon pairs. One photon is used for heralding the presence of the other in the interferometer. It is a Michelson-Morley interferometer. And then we perform also an interference experiment with single photons and two detectors. And you get then, when Charlie changes here the settings of these mirrors, and thereby it changes the length of this path and the length difference between these two paths, then he changes the phase, and then you get, by changing the phase, you get the characteristic interference sine curve for the counting rates of this detector and the complementary one for this detector. For instance, if Alice detector counts 60%, 30%, then Bob's detector counts 60%. Now, even Charlie can change the position of this mobile mirror, and so by changing this position he produces a change in the counting rate of Alice detector according to this pattern. Obviously, he produced also the counting rate in Bob's detector changes correspondingly too. Thus, you can say there is a correlation between the event of changing this mirror and the event of change in the counting rate of this detector. You have two events, Charlie changing the mirror and the change of the counting rate in the detector. And this correlation between these two events is independent of the observer's frame. This correlation exists in any frame, independently of the state of movement of the observer. And additionally, the time order of these two events is also the same for any referential frame. Both events are time-like separated. And this is usually identified with the principle of causality, when it says the cause precedes the effect. By tying causality to time, one claims that Charlie is the cause and the changing in the counting rate of detector A is the effect. It is similar as what it happens when I turn the lamp on and off by pushing this button here. I have the feeling to cause the lamp to light on and off. The equations describing correlations in classical physics, correlations between time-like separated events, contain time and space as variables. And they figure out that something material like a current is going on continuously from C to A, or from the switch to the lamp, from the switch to the lamp. A current going continuously through some cable from the switch to the lamp. And since the correlations are independent of the observer's frame, the equations ought to be invariant under change of coordinates frame. By applying this principle to the equations of mechanics, Einstein discovered the celebrated equality E equal mc squared. In the time-ordered relativistic causal view, the concept of energy is paramount, and the technological correlate is nuclear technology. Also, the quantum mechanical Schrödinger equation, which gives the counting rates, should be invariant under change of coordinates. By applying the Schrödinger equation describing the evolution of the statistical distribution of outcomes in time. This equation should also be invariant under change of coordinates. And by applying this principle, actually the principle of causality, Paul Dirac predicted the positron. So you see, because of the successful time-ordered causal view, it is tantalizing to assume that any correlations require a description in terms of equations with the variables, with the coordinates of time and space, and try to apply this principle to the quantum non-local correlation between the detectors A and B. However, this attempt fails. You cannot describe these correlations by means of equations in space and time. The time order here depends on the observer's frame, according to the state of movement of the observer, because these two events are the decision at these detectors are space-like separated, then according to the state of movement of the observer, the time order will change. In this case, you cannot say that one event, say Alice's decision, is the cause of the other, of the decision of detector B. In fact, there is no equation describing the quantum correlation between A and B, as if something is going on in the space-time from A to B or from B to A. Such an equation doesn't exist. But nonetheless, and this is crucial, the correlation itself remains independent of the state of movement of the observer. The observer will always observe, will see that if one detector counts, the other doesn't count, independently of how fast the observer is moving. So the quantum correlations are physically real, but come from outside the space-time. They cannot be explained in terms of a mechanism in space and time. There have been many attempts to do this. I myself have proposed, together with Valerio Scarani, one explanation model called the before-before model. And this explanation model and other similar models that attempt to explain the correlations introducing a mechanism in space-time, they have been refuted by experiment, and they lead also to conflicts with relativity. So the view that these correlations cannot be explained by a mechanism in space and time, this view has important philosophical implications. I have discussed such implications in other lectures, but it has also technological applications as well, important technological applications like quantum cryptography and quantum computing. And it is worth to stress this fact, because the mainstream view is that true physics has to be able of being technologically implemented. So, the main concept in this new context is no longer energy, but information. Information. Quantum information technology is possible because of the qualitative equation information equal randomness plus non-local coordination. It is this fact that is at the basis of quantum information technology. Suppose this experiment here again. I will now say if Alice detector counts, I put here an A, and if both detector counts, a B. So, and we have many runs, so we will get the outcomes will be a long sequence of bits, a bit string, A, B, B, A, B, A, B, B, and so on. this means that right here, this means A will be in the fourth run, Alice detector clicked, in the fifth, Bob's detector, and so on. Quantum physics, the rules of quantum physics, the equation of quantum physics, tell us that, for instance, in this case, we have to get here, we will get here for many runs, in the long run, 50% of A's and 50% of B's. But about this order here, in which order the bits come out, about this order, quantum physics tells nothing. And this sequence here is not fully random, because remember, the production of each bit involves non-local coordination. So there is no pure randomness here, but there is randomness and at the same time non-local coordination. And this is why you can say here there is information. And in fact, you can use this for the quantum technologies like cryptography. And this is the basis of quantum information technology, that you are producing bits by means of non-local coordination, of coordination coming from outside the space-time. Actually, this sequence here could very well represent the digital transcription of a masterpiece of literature, say, of Dante's Divina Commedia. This would be quite possible. You can say it's very improbable, but this is not in contradiction at all with the principles of quantum mechanics, because quantum mechanics doesn't establish how long is the long run. You can say, well, this does not happen in the lab. Yes, but it happens in our brains. When I am speaking to you, for instance, now, I am moving the lips, and these corporal movements are guided by my free will, by I am formulating, I am expressing, uttering information, and the energy for these movements is a material ingredient, and this comes from what I have eaten and so on. But the order which makes the information I am transmitting to you, this order requires non-material influences, requires this non-local coordination. By means of this non-local coordination in my brain, I am now formulating, I think, ideas that are not registered, not stored in the space-time since the time of the Big Bang. So we have two types of correlations: time-ordered correlations and timeless ones. How can we provide a unified description of these two fundamental facts. We have already said we cannot do this by trying to formulate these correlations by equations containing the coordinates of space-time, by a mechanism in space and time. So let us go the other way around. And we try to unify these two fundamental facts by getting rid of time and stressing that the very thing of causality is the correlation, not the time order. The correlation, so, reveals a causal relation, but the cause is not within the space-time. If one consequently applies this way of thinking, one should also conclude that time-ordered correlations reveal a causal relation, but the actual cause itself is outside the space-time. Changing the mirror is a condition for changing the counting rate. Pressing this button is a condition to turn the light on and off. But the cause is not that a material fluid propagates continuously in space and time from C to A, or from the switch to the lamp. You see, this view fits well to the argument that the space-time is not continuous but granular or atomic, which is an idea coming from quantum gravity. Actually, there cannot be any material connection or signal going on between two time-like separated events simply because there is no continuous space-time in between. In other words, nothing can actually travel from C to A, nothing material, or from switch to the lamp, because, so to speak, the road is interrupted everywhere. And therefore, one event cannot be the cause of the other. There is a causal relation, but the real cause is outside the space-time. It is a bit like the programmed movements you see in the screen of your laptop or your desktop. You have the impression that a dot is traveling continuously from one point to another point of the screen. But this is an illusion. Actually, there are series of pixels lighting subsequently. An electron moving from A to B is appearing and disappearing all the time. It is worth to note that this discreteness of the space-time saves general relativity from being destroyed by its own prediction, that is, the black hole singularity. In technical terms, you can say that all correlations, these correlations between time-like separated events, and the quantum correlations between space-like separated events, that these correlations are covariant or Lorentz invariant. They do not depend of the state of movement of the observer. They remain as correlations invariant under transformations of the space-time coordinates. In the case of the quantum correlations, there are no equations describing these correlations, but the correlations as such are invariant under any transformation of coordinates. So the space-time is not an arena where the events take place. The space-time itself is an event that emerges from outside the space-time. And consequently, the same holds for gravity, the curved space-time. It is an emergent property as well. To quantize a physical force or interaction means at the end to assume that there are phenomena related to this force or interaction that require influences coming from outside the space-time. This is the case for entanglement, but it is the case already for any single particle quantum experiment. To quantize the space-time means also to assume that the fabric of a space-time, the geometry, emerges from outside the space-time itself. And this amounts to say that matter and energy themselves are information after all, and come from outside the space-time. We could complete this equation energy and matter are also information coming from outside the space-time. To describe an interference experiment like this one, you rely pretty strongly on the concept of classical path. We are speaking here all the time about two paths, two arms of the interferometer. And in this sense, we are considering space-time like the arena where the play is going on. However, when you look at things more in detail, you discover that the classical path you are assuming is not that much classical or continuous, but it is granular. Again, in this point, quantum physics and relativity imply each other. You cannot have one without the other. If one considers only ingredients lying in the space-time, then one can say that the universe comes out of nothing. However, not all what matters for the physical reality is contained in the space-time, and hence the correct statement is that the universe comes out from information lying outside the space-time at the time of the Big Bang and at any time thereafter. In conclusion, the principles running the material world, like the conservation of energy, would not work without non-local immaterial influences. The visible world is not made out of what is visible, but comes from an invisible realm. The visible world is information coming from outside the space-time, like words uttered by invisible speakers. In words of the French poet Charles Baudelaire, la nature est un temple où des vivants piliers laissent parfois sortir des insondables paroles. L'homme y passe à travers des forêts de symboles qu'il observe avec des regards familiers. Thank you very much for your attention.